So I wanted to go over something called the singular value decomposition. So this would be the second topic that I posted about linear algebra. And the first topic I posted was just on eigenvalues and eigenvectors. And this topic actually has a lot to do with that, which we'll see later. But I wanted to post this because I think it's probably one of the most important and fundamental decompositions that we can do in linear algebra. And it's certainly gained a lot of popularity and seen a lot of use in the past 50 years as a method for data analysis and other things, which I'll go over. But I think if there's one topic that you're sort of just skimming through on linear algebra that you're interested in learning, I would say it's good to look at singular value decomposition. Besides just being extremely useful, I think that this is also sort of like, in a way, it's like the fundamental theorem of linear algebra, in the sense that the definite integral encapsulates the fundamental theorem of calculus. Basically everything you might learn in an introductory linear algebra course is used in this decomposition. And before we get into the computation, I guess I just sort of wanted to go over the big picture, this idea of why it is a fundamental part of linear algebra. Just mention its applications real quick, and then we'll go into some actual calculation. I will warn that this video might be kind of long. When it comes to doing a singular value decomposition by hand, it is certainly not a, I wouldn't say it's hard, but it's certainly not an easy task computation-wise. It's a lot of grunt work, but I'm even going to try to skip some of that so that we don't have to sit here forever watching us do basic arithmetic and row operations. But I will warn that it does take some time just to actually do the computation and go over everything because it's pretty broad. But essentially, this is a matrix decomposition. So if you're familiar with matrix factorizations or decompositions such as QR, LU, or how to diagonalize a matrix, you'll understand this idea of taking a matrix A and expressing it as a product of other matrices. So QR factorization has this, or we have the LU decomposition, things like that. So what is the singular value decomposition? Well, I'll just give it to you right away, and then we'll go over what everything means. So some matrix A can be expressed as a product of three other simpler matrices, U, sigma, and V transpose. And so I'll get into what all three of these matrices are. But what this decomposition really revolves around is this idea of the four fundamental subspaces that we see in linear algebra. So I won't go over them in too much depth, but just so you can recall, we have the row space. So that would be the set of all vectors x such that ax is non-zero. And then we have the null space of some matrix A, which would be the set of all vectors such that ax is 0. And then we'd have the column space of A, which would be a set of vectors such that A transpose Y is not equal to 0 or is non-zero. And then we have the left null space of A, which would be the set of all vectors Y such that A transpose Y is equal to 0. And so this idea of these fundamental subspaces and then the actual orthogonality of these subspaces is really what the singular value decomposition breaks down into at sort of a high level or pure level. But also it's better to think of it as this idea of how matrices encapsulate linear transformations. That should be something that we sort of develop after doing linear algebra. At first we're introduced to a matrix and we're like, oh, it's a rectangle of numbers, and so this would be a 2 by 2 square matrix, and we can do operations with them. We can multiply. We learn facts like AB is not always equal to BA, matrix multiplication doesn't commute like real numbers do, and things like this. And we know, oh, well, we can express vectors as linear combinations, but really the whole idea behind linear algebra is this idea of subspaces and then linear transformations, and matrices really are used to encapsulate linear transformations. And so at a very basic idea, the singular value decomposition relies on this idea of the matrix, of course, encapsulating linear transformations, and then this idea of dimension reduction. So if we were to just have some linear transformation from like R3 to R2, this is this idea of reducing a more complex matrix into a product of simpler matrices that might be square, as we'll see in this decomposition. Okay, what else do I want to go over to? Quickly, I'll just mention the applications. This video really can't get into the applications. That would have to be a completely different video. But of course, like everything you learn in math, or at least things like calculus and linear algebra, there is real-world uses for it, which is why it's important to understand the math of it. But specifically for singular value decomposition, this is used a lot in image compression. Mainly this numerical idea of expressing, or I guess an iterative idea of it, expressing the singular value decomposition as some numerical method, which is generally given by this sum. Let's see, the sum from I equals 1 to k. We'd have the singular value sigma, the basis vectors u, and then the transpose of the basis vectors t, v transpose. So this is essentially just another way to rewrite this decomposition, actually. So I'll just group these together. But also it plays a big part in data analysis, especially with PCA, or principal component analysis, which is probably the most famous, I guess, application of the singular value decomposition. And the principal component analysis is a direct translation of the singular value decomposition. It relies directly on this idea of orthogonal matrices that we see in the decomposition, and that itself is a linear dimensionality reduction technique. So what is the big picture of the actual decomposition itself? Well, the reason it's so important, and the reason I'm stressing it so much, and the reason that everyone learns it, is because we can take any real or complex valued matrix, so it's not just limited to the real numbers, and we can decompose it into a rotation, stretch, and rotation. So by that I mean that this is an orthogonal matrix, it's a rotation as far as a linear transformation goes. This is a diagonal matrix, this is a stretching or a scaling factor, and then this is also an orthogonal matrix, so it's another rotation. So we can decompose it into a rotation, stretch, and another rotation. And it generalizes the eigendecomposition of a square normal matrix with an orthonormal eigenbasis to any matrix. And so if those words are sort of confusing right now, I think when we actually start doing the computations and writing out what all three of these matrices are, it'll become a little bit more clear. But that's the big idea of the singular value decomposition and the applications. So I would say it's important to remember rotate, stretch, and rotate. And we'll get into a little bit more what that means. Okay, so we have this decomposition, A equals U sigma V transpose. So really the next question is, well, what does all of this mean? At least what is U, what is sigma, and what is V and V transpose? So U is orthogonal. So it's an orthogonal matrix, that's why we say rotation. Sigma is a diagonal matrix, specifically whose diagonal values are the singular values, which I'll get into what those are. But a diagonal matrix is, of course, elements only in the diagonal of the matrix and then 0 everywhere else. And then V transpose is orthogonal again. So we have orthogonal, diagonal, and orthogonal. And the important thing to remember is, we want to recall this idea of orthogonal matrices. So we say that a matrix is orthogonal if some matrix Q is orthogonal if Q transpose Q is the same as Q transpose, which is then in turn the identity matrix. So this idea that the product of the transpose of a matrix and the matrix itself is equal to the identity matrix, and then we of course want it to commute. Okay. So let me do a little bit more illustration. So we have A, our original matrix, and then we have the basis vectors U. So I'll do the this case of two vectors. So U1 and U2, which form the orthogonal matrix U. And just so we're clear on the arrangement here, we could do these dashed lines. So these make up the columns of U. And then we have sigma, which is a diagonal matrix. And in this 2 by 2 case, it would be composed of the singular values sigma 1 and sigma 2 and 0 everywhere else. And then V is another orthogonal, or this is V transpose in this case, is an orthogonal matrix with the basis vectors V1 transpose and V2 transpose. And so of course, because it's the transpose, the direction, the rows and the columns are going to be flipped. So our direction is going to be just like this. Okay. And I'll do this now. So A can be any matrix. So we'd say that's M by N, rectangular. So really, if you've done other factorization methods, you probably notice that sometimes we need it to be square, or we can't have a sparse matrix. Things like this. We need some fine-tuning in a way. And especially for eigenvectors on their own, eigenvectors are limited to square matrices only. So we can't compute the eigenvectors of a rectangular matrix. And that's why this method is so powerful, is because we're taking a general matrix, M by N, so the columns and rows do not have to match, and we're decomposing it into the following. So this matrix is M by M rather than M by N. Alright. Hold on here. Sorry. M by N, and then we have M by M, and then this is M by N, and then this is N by N. So this is the factorization. So this would be the dimensions of these matrices. And as you can see, even if we have some really general matrix A, and the reason that's important is because in the real world, we're often not dealing with square matrices. We're often dealing with rectangular matrices, especially for data, just because it oftentimes doesn't work out that it's perfectly square. We have 2 rows and 2 columns. We might have 2 rows and 3 columns. So the singular value decomposition is so general. That's just, at a very high level, that's why it's so important. It's so general that it can be applied in pretty much every single case. And so then what we end up with is this matrix sigma, which contains the singular values, but more importantly, we can compute the eigenvectors and eigenvalues of A, considering A transpose A, which we'll go over, and AA transpose. Rotate, stretch, rotate. So I'll also just list out briefly what these vectors are. So u1 and u2 are the singular vectors, is what we generally refer to them as. The singular vectors. And then sigma, in this case sigma 1 and sigma 2, are the singular values, which we'll go over what the actual singular values are. And it's important to note that the singular values are ranked generally, this isn't always the case, but generally we rank them in this descending order. So the first singular value should be larger than the second singular value, and this should go on and on and on. Okay, so let's just go over a little bit of some matrix arithmetic to sort of develop these equations and this intuition behind actually finding out what U, sigma, and V will contain as far as the decomposition. So when we have a matrix A, how do we actually calculate U? How do we calculate sigma? How do we calculate V transpose? So let's consider our decomposition. So we have U, sigma, V transpose. So what we want to look at is A transpose A and AA transpose. If you recall diagonalizing a matrix, we need this. We want to compute the eigenvalues and eigenvectors for this matrix, A transpose A and AA transpose. So let's consider A transpose A. So what will that be? Well, we know that A is equal to U sigma V transpose. So we have the transpose of that. So let's see, that'll be V sigma transpose and then U transpose. Okay. And then we'd have times A, which is U sigma V transpose. And so this is what we want here. These, we know that U is an orthogonal matrix. So this U transpose times U here is simply going to reduce to the identity matrix. So this is going to just become I, which I, in the case of matrix arithmetic, is just, it is the identity. So it's the matrix equivalent of the number 1. So essentially, this term will just cancel out from our equation. And so we'll be left with the fact that A transpose A is just V times sigma transpose times sigma times V transpose. And now we're just left with our diagonalization form, something that we've seen before, or at least I hope you've seen before. So this is A transpose A. And do notice that we can't do the same thing and reduce this to the identity matrix because sigma in this case is not orthogonal. It's a diagonal matrix, so that just does not apply. So this just has to stay as sigma transpose times sigma. And though V and V transpose are both orthogonal, we can't do this because they're not next to each other. And we need to be very careful about how things commute in terms of matrices. So we can't just move this over here and turn this into the identity matrix. So this is our form, our general form for A transpose A. So I'll just circle that for us. And this will be important later when we're actually going over an example that I have. But for now, we just want this. So what did we do? Well, A was originally an m by n rectangular and very general matrix. So A was m by n and general. But when we looked at A transpose A, this gave us a, which generally referred to as a positive semi-definite matrix with orthogonal eigenvectors and positive eigenvalues. So A transpose A yields, I'll just say P, S, D with ortho eigenvex and pos eigenvalues. vals. Yeah. So it yields a positive semi-definite matrix with orthogonal eigenvectors and positive eigenvalues. Okay, so what this really tells us is that so lambda, our eigenvalue for A transpose A, is really the square of our singular value sigma for A, for our matrix A. And this implies then that our singular value sigma is just the square root of the eigenvalues for A transpose A. Okay, and this is what we need to find sigma, our matrix sigma. We know that sigma is composed of the singular values, and this is what the singular values are. Given a matrix A, the eigenvalues associated with A transpose A is in turn the square of the singular values for A. So once we know the eigenvalues for A transpose A, we can simply take the square root of those. So then the singular values simply become the square root of the eigenvalues for A transpose A. Great. So this is what we actually need for our computation. And similarly, I'll show you very quickly how we find AA transpose, because we of course need both cases. And this is a very similar process. We're going to get something slightly different, but this actually just sort of gives us options for which matrix we want to calculate first in terms of U and V, and what V and U actually represent. So we had A transpose A, now we have AA transpose. So we know that A is U sigma V transpose, and then A transpose is going to be, let's put a parentheses here, it's going to be V sigma transpose and U transpose. And then right here we know that V is also orthogonal. So in the last example we had U transpose times U, but now we have V transpose times V. So this simply reduces again to the identity matrix, which just essentially is 1. So we find that AA transpose is U sigma transpose U transpose. So we ended up really with the exact same form. The only difference is now that A transpose A gives us the orthogonal matrix V and V transpose, and then here we get U and U transpose. So this will give us essentially another formula for whether we decide to compute U first or V. And more importantly, it tells us that V is the eigenvector matrix, for A transpose A, and U in turn is the eigenvector matrix for AA transpose. So eigenvector matrix for AA transpose. Okay, so I think we pretty much have everything that we need to actually go over an example. So I guess we'll just do that now. So let's consider, here we go, I'll just do it here. It's an example. So let's consider a 2x3 rectangular matrix given by A, whose values are 1, 3, negative 1, 1, 3, 1. And we want to find the singular value decomposition for this. So let's just write out what we have really. So we have a 2x3 matrix A. We're going to decompose into U, sigma, and V transpose. Okay, so U in this case is going to be 2x2. Sigma is going to be 2x3. And then V transpose is going to be 3x3. if we recall, U should be M by M, sigma is generally M by N, and then we have N by N. Okay, and so now the first step we want to do is actually find the singular values so we can form sigma. So what we need to do is compute the eigenvalues and eigenvectors of A transpose A. Now, for some of this work, what I'm going to do is actually skip over just some of the monotonous computation, like the matrix multiplication and stuff, but I'm going to write it out, and you can feel free to check them with like a matrix calculator. It's just this video is already really long, and I hope you can understand at least why I don't want to by hand show every matrix multiplication and every full eigenvalue computation, etc. But anyway, so I'm going to do A transpose A rather than AA transpose. So you can do this either way. So this means that I'm going to find V first, our matrix V, and then we'll use that to find U. And so this is the nice thing, is that once we find either U or V, and then we'll have sigma, of course, based on the eigenvalues, we can find either one based on this fact and this fact that we found earlier, given what A transpose A is and AA transpose. Okay, so I want to find the eigenvalues and eigenvectors of A transpose A. So first of all, I need to know what A transpose A is. So let's actually just do that multiplication. So A transpose, so the rows are going to replace the columns, so we're going to have 1, negative 1, 3, 3, 1, 1, times our original matrix A, which is 1, negative 1, 3, 3, 1, 1. And so we're given 3 by 2, 2 by 3. So this is going to yield a 3 by 3 matrix. And I've already done the multiplication for this, but you can of course check it. But this will give us a 3 by 3 matrix: 10, 2, 6, 2, 2, negative 6, 6, negative 2, and 10. Okay, and this is what A transpose A is. So now that I have A transpose A, I can actually work on finding the eigenvalues for this. So this is just as simple as using the general eigenvalue formula that we know. So we're going to look at the determinant of A transpose A minus lambda I equal to 0. So we want the determinant of A transpose A minus lambda times the identity matrix equal to 0. Okay, so let's go through this. So we have the determinant of, and I'm going to use this notation of DET for the determinant. So we know what A transpose A is. It's this 3 by 3 matrix. And 3 by 3 is a square matrix, of course. If you haven't noticed, we can obviously do eigenvalue computations with a square matrix like this. Okay, so we have 10, 2, 6, 2, 2, negative 2, 6, negative 2, 10. Minus lambda I, so lambda, so 1, 0, 0, 0, 1, 0, 0, 0, 1. And this is equal to 0. So what we're going to end up with, once we do the subtraction, is the determinant of the matrix 10 minus lambda 2 and 6, 2, 2 minus lambda, negative 2, 6 minus 2, and then 10 minus lambda. Okay. And again, I have done this determinant calculation off screen, but I will at least set up the cofactor expansion so that you can, if you've never calculated a 3 by 3 determinant, I will show you at least how to set it up as a cofactor expansion. So we're going to take, so this determinant, because it's a 3 by 3, we want to turn it into a difference in sum of smaller 2 by 2 matrices. That way we can use the general determinant formula, which just gives us this cross multiplication, and we should end up with a polynomial. So we take this first element, so you can think of this as the ith column, the jth column, and the kth column. So we want to take the first element here of the ith column, so 10 minus lambda in this case, and multiply it by the determinant, and this time I'm going to use this bar notation, but this is the determinant, so this is the same as det, times the determinant of a smaller 2 by 2 matrix. And so what we do is we ignore everything in the ith column, and then we ignore the j and kth elements, and we just focus on all the elements of the jth and kth column here. So we're going to get 2 minus lambda minus 2, negative 2, and then 10 minus lambda. Okay. Oops, that's too tall. Okay, and then now we're going to subtract the second, so the first element of the second column, the jth column, oh, I didn't want to do that, which is 2 in this case, so we have minus 2 times the determinant, and again, we're going to ignore everything in the second column and ignore the first elements of the first and third column, and then just put everything else. So we'll have 2, negative 2, 6, and 10 minus lambda. So 2 minus 2, 6, and 10 minus lambda. And then we're going to add the first element of the third column, so 6 times the determinant of, we ignore everything in the third column, we ignore the first elements of the first and second column, and we take everything else. So 2, 2 minus lambda, 6, and negative 2. 2, 2 minus lambda, 6, and negative 2. And this is the cofactor expansion for a 3 by 3 matrix. And if you're wondering why these signs change, so why it's positive, negative, and positive, that's just a fact of the determinant. So in the case of a 3 by 3 matrix, the signs for the determinant alternate between plus, minus, plus, like this, and it goes on and on and on for all the other elements. So this isn't a video about determinants, of course, but from here we can just do this cross multiplication, so blah 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 times this, and now we should yield something. And I've done this off screen, but I've simplified this polynomial, so I don't want to do all this work. So we end up with lambda times lambda minus 16 times lambda minus 6 equal to 0. Great, so now we have a factored polynomial, and we can find our zeros, our roots, or in this case our eigenvalues. So we'll have lambda 1 is equal to 16, lambda 2 is equal to 6, and then lambda 3 is equal to 0. And I want to make my first eigenvalue, ensure that it's the largest positive eigenvalue, and lambda 2 is the second largest, and this is the smallest. Okay, so now we have the eigenvalues, so we just need to find the eigenvectors for each eigenvalue. Okay, I'm going to go to another page here. So now we're going to find the corresponding eigenvector for lambda 1 equals 16. So we want to just recall this idea of finding x equals lambda x. So we have a minus lambda I times x equal to the 0 vector. Okay, so I'm not going to do all the work again for this as far as the reduction goes, but what we're going to have is our original matrix 10, 2, 6, 2, 2, negative 2, 6, negative 2, 10, minus our eigenvalue, which is 16, times the identity matrix, so that'll be 16, 0, 0, 0, 16, 0, 0, 0, 16. And then all times our vector x, where x is the eigenvector that we're actually solving for. Okay. And how do we actually find the eigenvector? Well, we need to reduce this system into reduced echelon form, and then we can just solve it using back substitution. So this is the part that I'm going to not do the whole work for, but I will show you what we reduce it to. So we start out, so let's form our augmented matrix. So negative 6, 2, 6, 2, negative 14, negative 2, 6, negative 2, negative 6. And we want to augment it with the 0 vector, so that's just all elements 0. So we want to reduce this matrix so that we can have an easier time doing back substitution. So what this reduces to, after some off-page work, is 1, 0, negative 1, 0, 1, 0, 0, 0, 0, and then of course, because we just had the 0 vector, these all stayed 0. And we are in reduced echelon form because we have a whole bottom row here of zeros, which means we're in reduced echelon form. So now we can do back substitution directly. So if we were to do that, we'd have, so this is in terms of x, so we have x1 minus x3 equals 0, x2 equals 0, and then x3 is a free variable, so x3 will just be x3 itself. Okay, so I think I'm going to express this in terms of x3, so I want x1 to be equal to x3, x2 is just 0, and then x3 is x3. So now we have everything we need to construct the eigenvector. So our eigenvector is just a vector with 3 components, x1, x2, x3, and we've determined what each of those are. So we'll let x1 be x3, x2 be 0, and then x3 be x3. And now I want to express this as an actual valued matrix, so I'm going to express our free variable x3 as just some scalar multiple alpha. So if we just pull that out for now, we'll figure out what that is later. That'll be 1, 0, 1. And so this is our eigenvector x. But now what we really need to do is we need to normalize this vector so that we can actually get a value for alpha, and then because we're normalizing, we will divide by that value. If we recall this this equation, you might remember, that's what we're going to be doing. Okay, so the vector norm in this case, it's just the length of the vector, the magnitude. So that'll be the square root of the sum of the squares of all the components. So we have 1 squared plus 0 squared plus 1 squared. That'll simply just give us the square root of 2. Nothing we could do there, that's irrational, so we'll just leave it as the square root of 2. So that we say that our normalized vector v1, so this is going to be the basis vector for our orthogonal matrix V, so this is V1, so our first vector element is going to be our vector 1, 0, 1, our eigenvector divided by this. So in another case it'll be 1 over the square root of 2 times our eigenvector 1, 0, 1. So really we'll just do this multiplication. So this will be 1 square root of 2, 0, 1 over square root of 2. Great. So this is V1, so we found V1. So this will be our first column element for our V matrix. Okay, and then we do the same process for our second eigenvalue. So we have lambda 2 equals 6. We're going to do the same formula. A minus lambda I times x equals 0. 6 is going to be multiplied into the identity matrix. And so what we're going to end up with is matrix 4, 2, 6, 2, negative 4, negative 2, 6, negative 2, 4, and we want that augmented with our 0 vector so that we can reduce it. And I hope it's clear how I got here. This is the exact same process as before. We're using the exact same formula, and it'll just yield this matrix this time. Okay, so once again, I'm not going to go through all the work to put this in reduced echelon form, but what we end up with is the matrix 1, 0, 1, 0, 1, 1, and then 0, 0, 0. And of course, these all stay 0. And again, we have all zeros in the bottom row, so we are in reduced echelon form. And so now we can go into back substitution and actually find our second eigenvector. So we'll have x1 plus x3 equals 0 in this case. And then x2 plus x3 equals 0. And then x3 again is our free variable, so that's just going to be, we'll just say it's equal to itself. Okay, so I'm again just going to solve this in terms of x3. So x1 will be equal to negative x3. x2 will be equal to negative x3. And then x3 is x3. So now we have them all in terms of x3. So let's find our eigenvector. This will be in terms of x1, x2, and 3. So x1 is negative x3, x2 is negative x3, and then x3 is x3. And then again, I want to pull out some scalar multiple, so I'm going to call it beta this time. And when we pull it out, we'll get negative 1, so negative 1 and 1. So now we just need to normalize this so that we can get a value for beta and have our basis vector v. Okay, so we do the exact same thing again. We're going to normalize it. So we want the norm of v2 is going to be the length again, sum of the squares, so it's going to be negative 1 squared plus negative 1 squared plus 1 squared. So this will just give us 1 plus 1 plus 1, so we just get the square root of 3. Again, nothing we can do with the square root of 3, so we'll leave it like that. So v2 is going to be 1 over square root of 3 times our eigenvector, negative 1, and 1. So if we multiply 1 over square root of 3, we're going to get negative 1 over square root of 3, negative 1 over the square root of 3, and then positive 1 over the square root of 3. And so this is our second basis vector v2 in this case. So we found our two vectors. Okay. v2, nice. So for v3, I'll split the page up here. For v3, our eigenvalue is 0. So this is going to be slightly simpler as far as the initial calculations go. So lambda equals 0. So again, we use the same equation, a minus lambda I times x equals the 0 vector. But in this case, 0 is going to cancel out the identity matrix. So we're just going to have to reduce our original matrix A in this case. So we have 10, 2, 6, 2, 2, negative 2, 6, minus 2, 10. Also, I've been saying A minus lambda I times x and using that for all of the eigenvector calculations. Do recall that A in this case is A transpose A. I've just been doing this because I'm used to the formulation, but this is A transpose A. Remember, A is not a square matrix. That's the decomposition we're trying to do. So just remember that. So this is A transpose A here, 10, 2, 6, 2, 2, negative 2, 6, negative 2, 10. And so we'll reduce that. So I'm actually just going to get rid of this. So, we'll set up our augmented matrix, 0, 0, 0. And we're going to reduce again. And I've done that off screen here. And what we end up with is the matrix 1, 0, 1, 0, 1, negative 2, 0, 0, 0. And of course 0 is still because of our 0 vector. Okay, so x1 and x2 are normal, and then x3 are free variables. So we'll have x1 plus x3 equals 0, x2 minus 2x3 equals 0, and then x3 is free, so we'll say that x3 is x3. So I want x1 to be negative x3, I want x2 to be positive 2x3, and then I want x3 to be x3. Okay, so now we can form our eigenvector x in terms of x1, x2, and x3. So it's going to be negative x3, positive 2x3, and then positive x3. And again, we want to pull out some scalar multiple. I'm just going to call it gamma this time. So we had alpha, beta, and gamma. And remember, these are just real numbers. And so if I were to factor it out, we just get negative 1, 2, and positive 1. And then again, the last step is we just need to normalize this so that we can find out what gamma is in this case. So we want the norm in terms of v3, so our final basis vector. So it's just going to be the length of the vector, so we have negative 1 squared plus 2 squared plus 1 squared. So we're going to get 4 plus 1 plus 1, so we're just going to get the square root of 6. And again, nothing we can really do with that, so we'll just leave it as a square root of 6. So then our vector v3 is going to be 1 divided by the square root of 6 times our original eigenvector, which was negative 1, 2, 1. Okay, so this comes out to negative 1 over square root of x, positive 2 over the square root of x, and then 1 over the square root of x. And this is v3. So we found all of our basis vectors for our matrix V, v1, v2, and v3. So now we can actually construct V entirely, because we know everything that it has. Okay. So if we recall, V is just going to be some matrix whose elements are going to be made up of our basis vectors, but we are looking for the transpose of that matrix. So really what we're going to end up with is having to take the transpose of it. So let's see here. V is just going to be columns, and in this case the transpose is just going to replace the rows and columns, so it's just going to be all along like this. V is going to be our matrix. It's composed of the basis vectors v1, v2, and v3. So in matrix form, this comes out to the columns of this. So we have 1 over square root of 2, 0, 1 over square root of 2, and then we have negative 1 over square root of 3, and then negative 1 over square root of 3, and then 1 over square root of 3, and then we have negative 1 over square root of 6, 2 over the square root of 6, and then positive 1 over the square root of 6. Okay, so this is V, so V transpose is simply this matrix with its rows and columns flipped. So we end up with 1 over the square root of 2, negative 1 over the square root of 3, and negative 1 over the square root of 6. And then 0, and then negative 1 over the square root of 3, 2 over the square root of 6, and then 1 over the square root of 2. 1 over the square root of 3, 1 over the square root of 6. Okay, so now we found V transpose. And so this is actually the brunt of our work. So after we found V transpose, we've pretty much found the rest of the decomposition. So the rest of this video's calculations will be much easier. We just need to use the facts that we developed earlier. So really, the most work you're going to be doing is at the beginning, if you decide whether to do the eigenvalues for either A transpose A or AA transpose, determining whether you want to find U or you want to find V. In this case, we did A transpose A, so we found V. After we know V or U, we can find either one very easily based on those formulas we developed. But first, we can actually develop our matrix sigma. So we recall that the singular values are the square roots of the eigenvalues for either A transpose A or AA transpose. So we found the eigenvalues for A transpose A. So our singular values are going to be given by, our first singular value is going to be the square root of our first eigenvalue, which was 16, so this will be 4. Our second singular value is going to be the square root of 6, our second eigenvalue, so that'll just be the square root of 6. And then there actually isn't a third singular value. The important thing is that the singular values we're only considering the positive eigenvalues of A transpose A or AA transpose. And so we ignore 0 or negative eigenvalues. So really we only end up with 2 singular values in this case because our third eigenvalue was 0. And of course we want the singular value, the first one, to be greater than the second singular value. So that's why I label this as singular value 1 and this is singular value 2. Great, now that we know that, we can actually form sigma. So if you recall, sigma is just going to be a matrix with the singular values in the diagonal like this. So in our case, sigma is going to be a 3 by 3 matrix. We recall it's m by n, so it'll be 2 by 3 in this case. So we have 4, and then 0, 0, 0, square root of 6, 0. Great. So this is our diagonal matrix. So we only have our singular value elements in the diagonal. So we found V transpose in sigma. So how do we find U? Well, let's recall what we were showing earlier, but let's take a different approach to it. So, if we took our decomposition, A equals U sigma V transpose. Let's try to solve this in terms of U. So if I wanted to get rid of this V transpose, I can multiply this by V. So we get U sigma V transpose times V. This would go away as they're orthogonal. So we'd end up with AV equals U sigma. Okay. So now this doubly implies, component-wise, that we're taking our matrix A and we're multiplying it by a basis vector, which is then equal to our basis vectors for U times our singular values for sigma. So we can do this one by one, and in this case we only have 2 singular values. So to find U, we could rewrite this as A times the basis vector V1 and set it equal to U1, the basis vector for the matrix U, times the singular value sigma 1. And then we can do this again for the second singular value. So A times the second basis vector for V equal to the second basis vector for U times the second singular value. And by doing this, because we're now dealing with vectors, we can rewrite this and find an explicit expression for this basis vector U, which we need to find. And then once we know those vectors U, we can compose our matrix U. Okay, so we want to solve for U. So let's consider our first one that we had here, U1 sigma 1. So U if we just divide through by things, we're just going to get u as 1 over our singular value times a times v1. So we can do this. So we're going to get 1 over our first singular value, which we recall was the square root of 16, which was 4, times this is our original matrix. So now in this case, when I'm saying A, this is our original matrix from our decomposition. So this is our 2 by 3 matrix that we started out with. So this is 1, negative 1, 3, and then 3, 1, 1. Times this column vector that we found for v, which is 1 over root 2, 0, 1 over root 2. And so now we've found an expression for u based on everything we already know. So we already know what our singular values are. We calculated those. We obviously know what our original matrix is, and then we know what these vectors v are because we already formed our matrix v by finding our corresponding eigenvalues and eigenvectors for A transpose A. So now all it is a matter of doing is doing this matrix multiplication, which again I will not do entirely here, but you can double check my work with a calculator. We end up with 1 over square root of 2 and 1 over square root of 2. So we end up with a 2 by 1 column vector. And of course we can see that because 1 over 4 is just a scalar multiple in this case, but we have 2 by 3 times a 3 by 1, so we yield a 2 by 1. Great. So now we found our first basis vector for u. So now we do the exact same process for this. So in this case, u2 is going to be 1 over our second singular value, sigma 2, times a v2. So our second singular value is the square root of 6. So square root of 6 times our original matrix A again. So 1, negative 1, 3, 3, 1, 1. And then times v2, which we know to be negative 1 over root 3, negative 1 over root 3, and positive 1 over root 3. And this will yield another 2 by 1 column vector as 1 over root 2, negative 1 over root 2. And this will form a nice orthogonal matrix with a reflection across each axis. Okay, so now that we have u1 and u2, we can go ahead and form our matrix U. So if we recall, U is just the matrix composed of the basis vectors u1 and u2. It's not transposed or anything. So those columns are just going to be those vectors. So we're going to have 1 over the square root of 2, 1 over the square root of 2, 1 over the square root of 2, negative 1 over the square root of 2. And now we found u. So this actually completes the entire singular value decomposition. And the best way to check this, or not, I wouldn't say it's the best way maybe, but it's the easiest way is, of course, if we were finding a decomposition, U sigma V transpose, once we find out our matrices, U sigma and V transpose, we could just multiply those all three together and we should yield our original matrix. And in this case, we do get that. So we found U, so 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, negative 1 over square root of 2, times our diagonal matrix sigma, 4, 0, 0, 0, root 6, 0, and then times our other orthogonal matrix, V transpose, which is 1 over square root of 2, negative 1 over square root of 3, negative 1 over the square root of 6, 0, negative 1 over the square root of 3, and 2 over the square root of 6, 1 over the square root of 2, 1 over the square root of 3, and 1 over the square root of 6, I believe. And if we multiply all three of these together, we get, so we should get back a nice 2 by 3 matrix that is hopefully our original matrix A. So here we have 2 by 2 matrix, we have a 2 by 3 diagonal matrix, and then we have a 3 by 3 matrix. So this 2 by 2, if we do it from left to right, I'll multiply these two matrices first, we should end up with a 2 by 3. So then we should get 2 by 3 times a 3 by 3, which will yield a 2 by 3 matrix. And in fact, this does. We end up finding out that that A equals U sigma V transpose, which then in turn equals our original matrix 1, -1, 3, 3, 1, 1. And so we have successfully found our singular value decomposition of our matrix A. A lot of work, I know, but generally we're not doing the singular value decomposition by hand like this, or really any of these matrix factorizations. We have computers to do them, but it is important to understand how to compute the singular value decomposition. So I hope this was helpful. Again, if you are confused on how I got any of these intermediary calculations, the reason I skipped over them is because I really did mean it. It is just grunt work for this stuff. Like it's finding determinants, just matrix multiplication, and eigenvalues, and that all just involves just a bunch of matrix multiplication, and I didn't want to go through finding a reduction for this whole matrix. But if you're at the level where you're doing singular value decomposition, you should be able to understand how to reduce a matrix, how to do back substitution, how to find an eigenvector and eigenvalue. So I hope that me not skipping those calculations was too much, but I also tried to include as much of it as I can. This whole idea of normalization, which is generally very simple, and then how we actually find these. And so the last comment I'll say, and what I've done before, is that you can do this either way. So I decided to do A transpose A. So I was in this realm. But you can do A transpose and find its eigenvalues. And in this case, it might have not mattered, but there might be a system where you're asked to find the singular value decomposition, and it might be easier, you think, computationally to find the eigenvalues of A transpose. But either way, you'll get the same thing. Just in this case, you'll find the orthogonal matrix U. And then you can use a similar equation to construct the orthogonal matrix V. But either way, your singular values will be the same. You should get the same eigenvalues for A transpose A and A transpose because they're orthogonal. So other than that, I hope this was helpful, and maybe you've come to appreciate the singular value decomposition a little bit more.